All right. Good afternoon, everybody. Welcome to day one of the press conferences at the 46th Annual DPS meeting here in Tucson, Arizona. My name is Dr. Vishnu Reddy. I am the press officer for the division, and we have a wonderful, exciting panel today. To my far right, we have Dr. Kate Sue. She's going to talk about the debris structures around an exoplanet system, and she's going to tag team with Sarah Morrison, also at the University of Arizona, who's going to talk about the planetary system itself. Then we have Dr. Marc Buie, who's a senior scientist at Southwest Research Institute, and he's going to talk about using occultation to study Trojan binary systems and the new discoveries he has made. Then we have Dr. Karen Meech. She's a faculty at the University of Hawaii, and she's going to talk about Comet pan-stars. And last but not the least, we have Dr. Alex Hayes, who's an assistant professor at Cornell University, and he's going to talk about Titan, Mare, and the depths of the seas on Titan. So without further delay, I'll ask Kate to come up and start the press conference. And please do silence your cell phones.
All right, thank you. My name is Kate Sue. I'm from University of Arizona. Our story is about this star called HD 95086, and we think that is a young analog of HR 8799, the first star that was found to have directly imaged 4 giant planets. And this research is funded by NASA through astrophysical data analysis program. So first about the star. The star is an early type star, meaning that it's much harder and more massive than our sun, much more luminous. It's pretty far away. It's roughly 300 light years away in the constellation of Carina in the southern hemisphere. An important fact about the star is that it's pretty young. It's only 20 million years old, compared to our sun, which is 4.5 billion years old. This is really an infant star. The star has caught a lot of attention in 2013 because it was found to host a 5 Jupiter mass planet at a projected distance of 56 AU from the star. AU is short for astronomical unit. It's basically the distance between the Earth and the Sun. Most importantly, the star also was known to have a lot of very bright infrared axis, indicative of a large amount of debris dust around the star. So why finding dust around star important? Well, before I answer that question, let me just show you what the planetary architecture of the solar system we know about. You will find that it's a very orderly structure. Closer in, we have a terrestrial planet, and further away, we have a belt of small body called the asteroid belt, and then we have 4 giant planets occupying a large space between the 2 belts. And then further away, we have a belt of small body called Kuiper belt. So the debris dust in those belts generated through collision among the asteroid, Kuiper belt object of the comet, they grow at the infrared wavelengths, and they are actually very bright and easily observable for a solar system that is far away. So astronomer has been using this debris structure to study the planetary architecture around other stars. And hopefully that we can answer some of the 2 outstanding questions about our own solar system, like did the planet form where they are today? Or why is the space between the planet so empty? Okay, so studying young systems like HD 95086 can provide a good look back at our own history. So that's why finding dust around young stars is very exciting. So as I mentioned earlier, using the data in the 80s, we know that it was thought that the star has a single small dust belt. But using the modern facility like Spitzer and Herschel, we can study the dust emission at multiple wavelengths. And using all this new data, we know that we think that the debris structure around HD 95086 has 3 components. The 3 components are a warm inner belt, analog to our own asteroid belt, a slightly bigger cooler belt, analog to our Kuiper belt. And most importantly, it also has a huge dust halo of fine dust enclosing these two inner belts. And discovering this halo around HD 950X6 led us to suggest that it is a younger analog of HR 8799, because we know that HR 8799 has three components in their debris structure. You also have a warm belt here, a cold belt, and encased by a huge disk halo of fine dust. Furthermore, the four directly imaged giant planet is occupying this empty space between the two belts in HR 8799. However, in HD 950X6, there's only one planet found so far. So in terms of the debris structure, these two systems are really very similar. The major difference is that HD 950X6 has more dust. It's consistent that it's a younger than HR 8799, so collision in their belts are more intense. You have more dust. So based on the debris structure we see in these two systems, we think that HD 950X6 is a young analog of HR 8799. Especially the huge dust halo that found in both systems suggests that enhanced collisional activity is a consistent behavior that we find for younger systems that are experiencing dynamical settling of gas giant planet and or delayed formation of ice giant planet. So we think that both systems are a scale-up version of the solar system when it was about 20 to 90 million years old. And finding an analog of HR 8799 is exciting because it suggests a common path on how a planetary system forms and evolves. So I will end here, and our next speaker, Sarah, will continue the story about HD 950X6 and tell you more about the possible planetary configuration.
Hi, so I'm Sarah Morrison. I am a fourth-year graduate student here at the University of Arizona, and this research has been funded by a NASA Earth and Space Sciences Fellowship. And so we've already heard about the debris system in HD 95086, so I'll be speaking about the planetary system and whether or not it, too, is a young analog of HRD 799. So the debris system, it's like HRD 799. It has several components: a warm belt, a cold belt, and a halo. And HRD 799, we know, is a system that hosts 4 directly imaged super Jupiters. We know in 95086 that there is a gap between the warm and cold belt, so between 8 and 80 AU, where AU is Earth's distance from the sun. And in order to have a gap, that means that there has to be something there that caused the gap in the first place, and that is continuing to maintain that gap, which sort of is a, what could that be? Currently, we know that there is one 5 times the mass of Jupiter planet that's in there at 62 AU, so we know that so far. And so what we have been looking at is what other planets can HD 95086 host, as well as could this planet be solely responsible for maintaining that gap? And so we use orbital dynamics to explain these observations and these constraints and predict where other planets could be and how massive they would be. So jumping right to our results, the currently known planet is very likely to be the outermost planet in this system, mainly because it appears to be shepherding that cold belt. So if you had planets that were outside, that were even further away from HD 95086, the host star, they would be within that cold debris disk and would be disrupting it, which is not consistent with observations. Also, to maintain that big gap that I was mentioning previously, planet B would have to be on a very elliptical orbit to be solely responsible. And we think that planets typically form on roughly circular orbits, so that would require an additional explanation as to how that planet got to be that eccentric to begin with. So it is certainly possible that HD 95086 hosts multiple planets in addition to the one that is currently known. But in order for these planets to have their orbits stable over the system's lifetime, which is about 20 million years, we find that while you can host 4 super Jupiters like you would in HRD 799, they would have to be of lower mass. So they would have to be less than 5 times the mass of Jupiter in order for them to be stable. And more broadly, what this research does is it offers predictions for future direct imaging campaigns as far as what we should be looking for and where we should be looking for it. And this, as Kate mentioned previously, this young solar system offers a glimpse into the past of our own and also puts our own solar system in a much greater evolutionary context. So as a summary slide, so the horizontal axis, looking from left to right, is going with distance from the host star. And what this is showing is a mock-up of where the other planets could be. So the black dots are where we currently know there are planets in our solar system. We know that the outer solar system has 4 giant planets. But you can see the relative sizes indicate their mass. They are typically a lot less massive than what we might expect to have in 95086. And then the red points are where, based on the fact that the orbits should be stable, and they should also not be disrupting the debris disks, where we would expect other planets to be. And so there are several possible configurations that you could have. But for the 4-planet case, which would be similar to HRD 799, your planet masses would have to be less than the 5 Jupiter masses. And also in general, if you have fewer planets, in order to maintain that debris gap, they would generally have to be on eccentric orbits, whereas when you have more planets of the same mass range, they could have circular orbits. And so, in general, what this shows is that this is HD 95086 is a sort of scaled-up version of our solar system, and it is certainly a system that we'll be learning more about in a few years with more data. Thank you.
Okay, and I'm Marc Buie from the Southwest Research Institute, and talking about something a little bit closer to home here. This is a double asteroid that's been known for a little over a decade now, called Patroclus and Menoetius, and reporting on some stellar occultation measurements that we made here. As usual with a lot of these kinds of projects, there are a lot of people involved. These are the co-observers and co-authors on the paper, and there's lots of other people that took data and helped make these results a reality. Just to give you the direct observational results from this project, here we saw an occultation, so it's about a 9th magnitude star that this object passed in front of. We got 36 stations with data, and 11 saw an occultation. Two objects were actually observed instead of just one, as the case for most asteroids. And we've determined that they have the same shape and almost the same size, but not exactly the same size. Patroclus, the slightly larger of the two, you see the dimensions of the object listed here, and you can see the slightly smaller for the secondary object. The more important thing that we've been able to derive from that by putting it together with historical light curve observations is that we can put new constraints on the shape of the object. And this 3-dimensional ellipsoidal shape. I give the numbers here, but the surprising and new information here is that it's actually an oblate spheroid, which the Earth is an oblate spheroid. It has polar flattening due to rotation. In the case of these objects, we don't believe that they're rotating fast enough to do that, but it's the same shape that we're talking about. And just submitted a paper to the Astronomical Journal on these results yesterday. So here's an overview of where all the people were scattered over the United States. Every dot represents somebody that had set up a telescope and a camera to observe this event. The red ones did not see the star occulted. The green ones did, and you can see 2 shadow tracks that are kind of overlapped, cutting across the central United States. You notice there aren't any dots in the middle, that's because it was a huge winter storm blowing through and kind of messing us up. I was at this green dot here in Durango, Colorado. Let me show you what I saw. So this is a video field frame showing the images I was getting in real time. In the upper right's a cartoon showing what's actually happening. In the upper left is a light curve. So you see, bingo, you hit the star, it goes away. And a few seconds later, the star comes back out again. And we use this measurement to get the sizes. So we put all of the observations together from this, and we can get a limb fit. Here's what, putting all the data together for Patroclus. Each one of these lines represents one station. The orange dots indicate where the star disappeared and reappeared in all these cases, and then the black line is the best fitting ellipse. This one's a pretty standard looking ellipse, nothing particularly worth mentioning in and of itself. Menoetius, this one actually slowed me down a little bit because there were two chords at the bottom where the observers should have seen an event and didn't. And I looked into all the implications of that. In the very end, turns out that they just missed seeing the occultation. And there really is a piece of an object down there. So we get these two sizes independently measuring the shapes, and it's nice to see that we basically got the same shape. The major axis of the ellipse points at each other, which is kind of what we expect for a tidally evolved system of this type. And just to give you an example, here's kind of what it looks like rendered at an equatorial aspect, which is not the same as the aspect at the time of the occultations. You'll see that there's definite polar flattening here, and there's a slight modulation in the width of the object as it rotates. Okay, so the fun part about this gets off into the implications and what this means for studying the outer solar system. I don't have final answers on any of this. These are kind of pointers to research and thoughts and things that we're going to be looking at into the future and the implications of this measurement. The shape is actually consistent with an object that was once rotating faster than it currently is. And the difference is right now it's rotating about once every 100 some odd hours, and that shape is consistent with an object that was once rotating once every 8 hours. The fact that the shapes are so similar is suggests, and similar sizes, there's a lot of long train of thought on this, but it suggests that these objects formed as a binary object as well. This one also has a lot of similarities in terms of the shape, structure, orbit periods, separations, all of that with another class of objects, the Kuiper belt objects out in the outer solar system, that we see a great many binaries that look just like this object. In fact, it has been pointed out by Morbidelli and others that the Trojan asteroids probably came from the Kuiper belt, and so we may have a direct genetic link between this object. It's kind of exciting because this one's much more accessible to us by various exploration techniques, telescopic observations, spacecraft observations. We could actually get out there and study this one up close much more easily than we can from something in the Kuiper belt. And this particular object, one final point I would make, is a great prototype event for the kind of observations that I'm trying to do with a new network of telescopes called RECON. TNORecon.net is the website for that project, where we're putting telescopes in schools all over the western United States, basically every 50 kilometers. And this is going to help us measure Kuiper belt sizes, but it's also going to tell us just how often and what the distribution is of binary objects of this kind. So with that, I will hand off to Karen Meech.
All right, thank you very much. Today I want to talk about some of the first surface observations of two objects that may be from the Oort cloud, and the scientific title of the talk that we'll have in the conference will be the Manx comets, Manx being a tailless cat. And this comet, both of these are almost tailless with very little activity. So this is an exciting result because we've never seen anything like this before. So let me start with the discovery of this object. The first one was discovered with the Pan-STARRS telescope shown in the upper left. This is a survey telescope on the island of Maui that right now is being funded by NASA to search for near-Earth objects. So it was discovered in August 2013. It was an asteroidal object, and very quickly they looked backwards into some of the older data, found more data, and were able to get an orbit, which showed that it looked like a long-period comet. Everybody jumped on this observation fairly quickly to try and see if there was any cometary activity, and some amateurs actually reported cometary activity, but larger telescopes weren't seeing it. And you can see from the image in the middle shows the object very unfortunately right next to a bright star, so you can't see any faint dust coming off of it. The next image shows, again, it seems to be right next to a star, and it's passing through a region of the sky with a lot of nebulosity, so again, hard to see any faint tail. We got some deeper, longer exposures with Canada, France, Hawaii 3.8 meter telescopes, still didn't show anything. So finally in early September we got director's time on the Gemini 8 meter telescope to see if we could see any cometary activity. So here's the images from those early observations. The one on the left shows the comet. You can see the scale at the bottom is about almost 44,000 miles across. You see a faint hint of dust extending to about the 10 o'clock position. There's very little dust here, and the image on the right is just a blow up where we've tried to remove all of the field stars. Now this is a very odd comet because typically long period comets that are coming in from the Oort cloud generally are very active with long tails at this distance, which was about the vicinity of the asteroid belt. This one was at about 3.4 AU. You can see the orbit of the object on the right. This is C 2013 P2 was its cometary designation, and it's named Pan-STARRS. In fact, just this September, a second one of these was discovered, and we immediately got on this one, and you can see the image in the center bottom. It too shows very little activity. Now, this is very unusual because most of these guys are typically very active. One that you're probably very familiar with, Hale-Bopp, at a similar distance. This shows the extent of its huge dust tail, although of course that one is a very large nucleus. So why is this so exciting? Well, there's a couple of reasons. Now, when the Oort cloud was first hypothesized by Oort in 1950, he realized a problem. He only had 13 comets, and he made a histogram similar to the one you see in the lower left, which looked at the orbits of 13 comets, and he saw a narrow spike suggesting that comets were out between 100 and 200,000 AU from the sun. And he thought this spike was too tall and too narrow, because the first time a comet comes through the inner solar system, it may or may not get perturbed by the giant planets and lose some of its energy. So the next time it comes in, it will have lower energy or a smaller orbit. So that red shaded area, there should be a lot of comets in there, and they were missing. So he thought maybe they're coated by a volatile frosting, which meant material that evaporated on the first passage, and so they were just lost. So maybe this is one of these things. The second idea, more recently with some of the new dynamical models of the solar system, Kevin Walsh with the Grand TAC model, you can see a figure from his Nature paper in the lower right, he suggested that when the giant planets migrated inwards in our solar system, they dragged icy material towards the sun, and when they migrated outwards, some of the inner solar system material got thrown outwards. So we wondered if maybe we're seeing the first evidence of some of this inner solar system material. So we got some data to characterize both of these objects. The first one, C 2013 P2, you can see a spectrum on the right-hand figure. And what we're looking at is its reflected light as a function of wavelength. It doesn't look like red Trojan asteroids. It doesn't look like red outer asteroid belt asteroids. It doesn't look like a comet. It's very red, much like Kuiper belt objects. So this would seem to suggest maybe it's like Oort suggested, a red outer solar system material that's just lost its volatiles. However, the second one, we haven't had time to get a spectrum, but we did get some colors. And the lower right panel shows, in comparison to the first object, P2, P2 is shown with the red dots. You can see the white triangles show the reflected light colors of our second object, 2014 S3, in comparison to inner solar system asteroids. And this is tantalizingly similar, so it looks like we may have the first evidence of some inner solar system material thrown out into the Oort cloud. So to summarize, it may be that the Oort cloud is populated with a lot of asteroids, something that some people have speculated on, but this might be the first case that we've proven it. It could be that there's a lot of this material in the Oort cloud. The sizes of these two objects, P2 is about 5.6 kilometers or so in radius. The other one's very small, only about 0.4 to 0.5 kilometers. If you assume they're all the larger size, there could be 1 billion of these in the Oort cloud based on the Walsh model and how much material could have been thrown out, and that could be 7% of the mass or so. And likewise, if it's confirmed the second one really is inner solar system material, this is exciting not only to see this stuff in the Oort cloud, but also that it's got dust surrounding it, which suggests ice. And we've never thought that these type of asteroids were icy either. So I'll just end showing some of the acknowledgments. This has been sponsored by NASA Astrobiology Institute and NASA Planetary Astronomy, and these are all of our collaborators. Thank you. Now, next will be Alex Hayes talking about Titan.
Great, thank you very much. Okay, so similar to the other speakers in today's press conference, I am simply a spokesperson for a much larger team, some of which you are actually sitting here in the room as support, which is thank you very much for being here. And some of the key players that are involved in the slides I'll be showing are shown here on the title slide. And I'll also point out that all the material that I'll show is also available on our group's webpage, www.alexanderghayes.com, and then you just click on the press/popular science section. So I'll be speaking today about some recent observations regarding Titan's lakes and seas made by the Cassini spacecraft's radar and VIMS instrument. So for generic background, Titan is the only moon in our solar system that has a thick atmosphere, and that atmosphere contains a significant fraction of methane, which acts in a volatile cycle very similar to our own water cycle, and drives both climatic and geologic processes that result in morphologic forms like dunes, lakes, seas, and rivers that have striking similarity to their terrestrial counterparts. And this really makes Titan an explorer's utopia. And Cassini just keeps surprising us with new observations and measurements despite having been looking at this moon for 10 years. And today I'm going to talk about 4 of them. And the 4 involve 2 different subjects. The first is the measurement of the depth of both the largest sea, depth measurements from parts of the largest sea in the north, Mare, and the largest sea in the south, Ontario-Lacus. And then an update on observations of these transient features that we've been seeing popping up in the northern seas that have been affectionately dubbed magic islands, and in fact, sometimes magical, mystical, mysterious islands. And so let's start with the depth measurements. This all started about a year ago when we had a paradigm shift in our understanding of how Titan's Mare work. And this came from the work of Marco Mastrogiuseppe, then at the Italian Space Agency, now research associate at Cornell University. And what he did is took an observation we had of Ligeia Mare obtained in May of 2013, where we actually turned the spacecraft straight down so that effectively the radar looked straight down at the surface of Titan and measured the time of flight, or the time that it took the microwave energy to leave the spacecraft, reflect off the surface of the liquid, and come back. And we planned that observation mainly to look for waves on the surface of the lake. But what we never thought was possible was what Marco found, which is when you process that data in the correct way, what you actually find is that here is a plot showing range from the spacecraft on the x-axis and the power that the spacecraft received on the y-axis, and you clearly see there are 2 instances of power that were returned from the surface. And the first one did correspond to the reflection from the surface of the sea. And the bottom one, which was just so surprising, was the fact that we measured the bottom of the sea. And the distance between these 2 peaks tells you the depth of the sea. And so this was the depth of Ligeia Mare, which is the second largest sea on Titan. And what's actually also surprising here, and the reason we didn't think that this was something we would have expected, is that in order to be able to see the secondary peak, that radar energy is going through a double 320 meters of liquid two-way transmit time, which means this liquid is amazingly transparent to the microwave energy and gives us very strong constraints on what it's made of. And by using these measurements that give you these depth measurements across where you've looked at that sea while looking straight down, you can actually calibrate some of the measurements we've been obtaining over the past 10 years and use them to make depth maps like this that show the depth of the entire sea and tell us that you're looking at about a volume equivalent to something like 3 times the volume of Lake Michigan, or more interestingly, perhaps 55 times the volume of all the proven oil reserves here on Earth in this one sea on Titan. Okay? Now, moving on to the point of the press conference, we had this observation acquired in August of this year where these results from Legia Mare really took us by surprise, and what I find amazing is that despite having been there for 10 years, we can still learn new ways to use the instruments on the Cassini spacecraft, and we actually went about retasking the way we're going to use the spacecraft based on this new knowledge that we can measure the depth of the seas. And this was our first retasking of this observation acquired in August, where we turned towards Nadir and took a Nadir track over the largest sea, Kraken Mare, and then turned back to look at a SAR image over Legia Mare, which we'll get to near the end of my discussion, looking at Magic Island. Now, what we found when we first looked across Kraken Mare is that for a majority of the sea, we did not see the depth. We didn't see the double peaks. But what we did notice is that the shorelines are extremely steep, and it suggests that they quickly may have gone deeper than the 200 meters, which is basically the limit of the detectability using this technique. Or the liquid was just more absorbing, one of the two. However, when we got to near the end of the track, over this drowned river valley that hits the northeastern end, or southeastern end, sorry, of Kraken Mare, we did actually start to see these double peaks and found that near this drowned river valley here, we were seeing depths between 20 and 40 meters leading into Kraken Mare. Now, I mentioned that we didn't think that we'd be able to see these bottom reflections, so we didn't actually process the data that was obtained as a Cassini Christmas present. Cassini gave us a Christmas present back in 2008 and gave altimetry data over Ontario Locus, which was used by folks at Stanford, namely Lauren Wye and Howard Zepker, to say that the surface of the sea was smoother than 3 millimeters over 100-meter length scales at the time of this observation. So we always tell people this is where you should go water skiing, but we were always worried about whether the boat would run aground or actually be able to operate. We didn't know the depth of the sea. But when you use this new technique that allows you to process this altimetry data, what you find is these secondary peaks exist. And so now, taking back data acquired in 2008, we were able to measure the depth of Ontario Locus and obtain depths again of 20 to 40 meters along this section of this particular lake in the south. Now let's move on to the second half of what I'd like to speak about, which is these transient features that apply in the sea. And they were first observed in 2013 at Legia Mare, which is the lake that I showed you the bathymetry map of. And in this August observation, we saw a transient feature that appeared at the same location. That's interesting because in observations between May, July 2013 and today, we had observations of that area that showed we did not see it. So this was a JPL image release, 2 weeks ago, that led to some news stories of the Magic Island mysteriously reappearing on Saturn's moon Titan. And so here's what the observations show. This is data acquired back in 2007 in the upper left. Then we have data acquired in July of 2013 that showed this 10-kilometer size bright feature that just popped up in the middle of Legia Mare off to near one of these real islands here. And then there is radar and VIMS data that was acquired in between, in this case here, July 26, just 2 weeks later, where we didn't see it. And then just this last August, it's back again, but looks a little bit differently. So we don't actually know if this is the same feature or if this is perhaps a different feature, and it's just some process that generates these things. However, what I also like to talk about today is this observation, which has not been released, and this is the other section of Kraken Mare. So this past slide was of Legia Mare. Now we're looking at Kraken Mare, which is the largest sea on Titan, and in August we observed new Magic Islands that seem to be cropping up in Kraken Mare. Here's a zoom up of it. And this observation is special because within 2 hours of looking at the radar observation, the visual and infrared mapping spectrometer, the infrared spectrometer on Cassini, also looked at the same area. And surprisingly, they also saw evidence for the Magic Island. So it was seen by both the radar and the VIMS instruments in August. And here is a plot showing, here's the radar observation, And this is where the magic island is. Now, the VIMS instrument is much lower resolution, but provides spectral information, which is very complementary. And what you can see is a strong detection shown here in the white box at 5 microns at the same location as the magic island. And what I'm showing down here is just a plot of this feature, subtracting the detection at the position of the magic island from an area over open sea. And the difference between them shows that you basically have a very strong 5 micron bright reflection occurring at the location of the magic island. And this kind of spectral behavior of a 5 micron bright reflection has been used by the VIMS team to suggest the presence of either waves or wet ground before, and really helps us interpret what these magic islands could be, or at least this one at Kraken Mare, because the only way to get this VIMS reflection at 5 microns is for the feature to be on the surface of the sea. So it can't be something under the liquid surface, and the two most likely scenarios to be able to see it in both radar and VIMS like this is either we're looking at waves, or we're looking at some kind of very smooth debris sitting on the surface of the lake, like you might expect to see if perhaps liquid was coating, you had wet solids that were floating in the sea. So those are the two most likely scenarios based on this observation. But this is exciting in showing us that these lakes and seas are dynamic. And as the sun continues to rise, moving towards the summer solstice in 2017, we hope to see a lot more dynamic phenomena occurring in Titan's Mare. And so just to sum up and remind you, we talked about 4 discoveries: the depth of the Drowned River Valley entering Kraken Mare and the depths of southern Ontario Lacus, as well as new observations of the Magic Island, including a reemergence of the Magic Island here at Legia Mare, and a new observation of a Magic Island that was coincidentally observed within 2 hours of the radar observation by VIMS. And slides and the JPL press release that should have been put up on the web at the coincident with my talk here can be found at www.alexanderghayes.com, and you click on Press Popular Science. And thank you again to both you in the room and the support folks from the Cassini Radar and VIMS teams.
Thank you, Alex. We'll open up for questions. Please state your name and affiliation, and then you can ask the question. Rick, you have here.
Leslie Sage, Nature. Marc Buie, so you had 3 missing detections of chords, station 17, 29, and 30. One missing detection might be careless, but 3 missing ones suggest to me that the shape is more elliptical than what you've inferred.
Well, number 17 is right at the limit of that limb. So I think that one is completely consistent with not being seen and also that limb fit that we had. So that one I don't consider to be a mystery at all. That one I think we're okay on. It's the other 2 that kind of bothered me for a while. I worked that particular problem pretty hard. If you sort of ignore what the geometry is at the time you're observing it, you could look at this and say, wow, maybe you've just got a huge impact basin on the southern pole of this object. And I actually worked up a shape model that shows, yes, you could actually have that consistent, but it requires you to have a look angle that's within a degree of the equator. And we can rule that out from the orbit. So once you put in the true sub-Earth latitude at the time of this event, which is like a minus 20 degrees, there's no way to create a void on the object that's consistent with the non-detections and yet hide it from photometry. So the only thing that I can say is that it was an incorrect report of a missed occultation. Unfortunately, the tapes that they used to record the data were written over before I could raise this point, and there's nothing other than the reports that they said, well, we looked carefully and we thought we should have seen something, but nothing was there. I'm using that as a reminder to the amateur community that, you know, if you want this to be taken scientifically seriously, you got to save the data in case questions like this come up the next month or 10 years later. But I have to rule this out as a valid missing measurement.
What was their readout rate?
These are all typically video cameras, so, you know, 30 frames a second kind of things, yeah.
Okay.
Hi, I'm Dan Briano with National Geographic. Alex, I wonder if you could say a little bit more about the 2 scenarios you put out for these islands. I make sure I understand. Are you saying that you just have you might have wave action in these locales that's creating this, or you might have essentially icebergs that are coated with liquid, or how should we write about these things?
Yeah, so the question was exactly how to interpret the Magic Island data, and the new data taken from Kraken Mare is really nice because we have both radar and VIMS information, which means we have microwave scattering and infrared reflectance. And the 5 micron bright signature that was seen by VIMS at this location requires you to have basically facets on the surface that are facing towards the instrument that are smooth to essentially the wavelength scale. So things that are smooth to the micron-ish scale, and that really would point to waves where you can have smooth liquid on the crests of the wave, or if it was solids, those solids would either have to be very smooth or wet, producing a smooth interface for that reflection to occur. And from the SAR data, because we know that the liquid is highly transparent, it was hard to effectively rule out whether the Magic Islands were a phenomenon at the surface of the liquid or something underneath the surface of the liquid, just underneath it. And the VIMS data allows us to do that, because if this was a submerged feature and you had a flat liquid on top of it, the VIMS would not have made a detection. Does that help?
Maybe I'll ask you more.
Sure.
Leslie Sage Nature for Alex. Are you able to rule out evaporative processes? Don Hunton made a case a few years ago that the lakes were made of ethane. And can you rule out that as the sun rises in the north, that you're not just seeing evaporation revealing features that were submerged by not very much?
So that is a good question. Well, there's a microphone, so you heard the question. The first point is the lakes are surprisingly not made of ethane. That was one of the discoveries from being able to see to the bottom of Legia Mare at 160-meter depth. To have the liquid be that transparent, it needs to be methane dominated. But methane is the volatile that might evaporate on you. And so that is a good point, that changes in liquid level could potentially cause these Magic Islands, and that's something that we considered. But the volume of liquid that you would have to remove in order to just change a surface area so large like Legia Mare or Kraken Mare over these timescales would just be massive and would be energy limited, and you wouldn't be able to change the depth of the sea more than likely, from evaporation at least, on that short of a timescale. Although other people have thought about tides or even winds pushing liquid away and revealing something that's just underneath the surface. And that is possible, but you have to think about it some, because in fact, this liquid is very transparent, as you can see by the radar seeing through 160 meters of it. And so just a little couple of millimeters of liquid would be transparent to the radar, and you'd still see the feature, unless it has a very unique makeup or composition. And so it's a complicated problem, and as a graduate student at Cornell University, Jason Hofgardner, whose PhD thesis will largely be contributing into the understanding of how these things might form. But regardless, the most interesting constraints so far are the new observations at Kraken Mare from both radar and VIMS, which really point to this being some kind of surface phenomena. And I would be hesitant to think that you could remove enough liquid to show up, have something show up that wasn't observed before, because it was too deep.
Tom, come back here.
Yeah, I'm Tom Beal with the Arizona Daily Star. I have a question for Kate and Sue, or Sarah, I'm sorry. You propose this baby solar system as a good place to look for exoplanets. Are you proposing it for whom and by whom? From space, from the southern hemisphere, from a medium-sized telescope, from a large telescope? Do you have somebody in mind?
Okay. So there have been some looks at this system already in terms of trying to find planets, and there's that one that is currently known that's 5 times the mass of Jupiter. But we also have detection limits based on those previous ones, as in terms of what they should have seen if there were planets that were more massive. So one of the surveys, I think, was with Gemini, wasn't one of the
VLT.
BLT. Okay, so BLT had a detection of this planet B, and the detection limits are currently at. They should have seen an object that was upwards of 21 times the mass of Jupiter within up to 16 AU from the star. And then there's also detection limits that they should have seen something that was above 7 Jupiter masses to 30 AU from the star. It gets more difficult as you get closer in, of course. But I think in the future, especially as technology improves, that once you can get closer into the star at high contrast, because the star is a lot brighter than your planet usually, then you'll be able to detect more. So I think in the future, this system will be is of interest to. I know of several groups that are actively looking for more planets in the system currently, and in the future there will be as well. So as far as professional astronomers, to answer your question more directly, there are quite a few people that are currently looking at the system, looking for more planets.
Using the ground-based telescope.
Using ground-based telescopes mainly, because it is possible to. That the original detection of Planet B was done with ground-based telescopes.
Okay, Dan?
So, Kate and Sarah, I also was wondering if you could say a little bit more about the analogies you see between these two systems and Earth's solar system. I mean, what does this tell us about planetary formation? If this is a standard model for, sun-like stars to form these things, if that's the case, if that's what you're saying.
Yeah, well, that's basically our story. I really think because we have found so many exoplanets through all the other methods like transit, radial velocity, and you found a lot of diversity in the exoplanet. Half Jupiter, half Neptune, all the things. Those are the things that we don't have in our solar system, right? So you're sometimes wondering why our solar system is different. But if you look at the star we're talking about, the sibling, what I say, they are really pretty similar. So that's really suggesting that it has to be a common path how a star formed, even though they are more massive than our sun. But in terms of the structure, they're pretty similar. So I believe that there has to be something that's really telling us about how general in our solar system form. And for other exoplanet system, we just haven't found the exactly similar thing like our sun. So,
Also, to add to that, when the 4 planets were discovered in HRD 799, they're of such high mass that originally it was a puzzle as far as how you could form that many planets of that high mass. And the fact that we have at least found that the debris system in these two systems is fairly similar, and it could be that the planets are also similar, could imply that whatever happened in HRD 799 might not be as rare as we thought.
Okay.
Hi, Chris Crockett from Science News. I'm sure you saw last week the beautiful image from ALMA of that disk around HL Tau with the thin grooves. I was wondering if you could help maybe put that in context, your observations in context with that system, in particular, how we see the thin grooves at a million years and this wide gap at 20 million years. Does that help piece together an evolutionary sequence for how giant planets build and help constrain the timescales for formation?
Do you want me to take that, or do you want?
Sure.
Okay. So that system was a lot younger. That was essentially a protoplanetary disk, whereas here we're looking at a debris disk. So we're looking at a later stage of evolution. So most of the gas, so that system probably had a lot more gas in that system, whereas HD 95086, we have some limits on the gas in that system, but it's thought that it's nowhere near as gas rich as that one would be. So this, in HD 95086, we have a lot wider gap, whereas in the HL Tau, they were very narrow. So this, placing the HD 95086 in sort of that stage would be that planets would have already formed, so the protoplanetary disk is essentially gone. But you have a lot of parent bodies that still crash into each other so to produce debris. So the debris disks are there. But probably a lot of the gas is gone, and the planets should have already been formed. However, In our own solar system, we think that this would be around the time that our giant planets were migrating around. So there could be some interesting dynamics involved there, where your planets in 95086 are either currently undergoing migration or have stopped migrating and produced that wide gap. So that would be a later stage, whereas in the HL Tau case, that's more that the planets might still even be forming in that stage.
And I want to add that we are going to get our observation on HD 95086.
Yeah, so stay tuned in a year or so.
Yeah, that would be very exciting.
If I could ask just a quick follow-up too, how does HD 90586, the star itself, compare to HR 8799, both in age and just in general properties, and can that shed any light on any differences between the disks? I did notice it looked like the 8799 disk extended, or the halo extended much farther.
Because they're at different distance. Actually, I have a comparison table in my slide, if you can go back to that. So HR 8799 is much closer. So we are really talking about sensitivity limited. You know, the fan halo is dropping so steeply as you go far away from, will be the last slide in the actual, yeah. So, one more, two more. I actually have a table if you care. So in terms of the stellar property, you know, the mass of the star, luminosity of the star, they are really similar. But HR 8799 is slightly older. We think it's roughly 50 million years old. And the HD 95086 is roughly 20 million years old. But in terms of the debris structure, you know, where the astrobel, where the kettlebell, and the disk halo, they are roughly similar. But the big difference is that the dust amount of the dust in the younger system, HD 95086, is much more. They're much more. In terms of the mass, it's roughly 2 times more. In terms of the luminosity of the dust, it's roughly 10 times. So that's consistent with that. It's being younger than HR 8799.
Thank you.
Okay, Leslie? Sure.
Leslie Sage, Nature, for Kate and Sarah. So if I remember the Grand Tack correctly, the migration was happening around 2 million years to suppress the size of Mars. And that's much younger than what you're talking about here. And of course, the sun is much less massive. So is the size of the debris disk and the amount of dust, do you think that is going to end up correlating with the mass of the star? Or is it more independent according to the grinding scale of the solid bodies that are being formed?
So one might expect that early on, when you have your protoplanetary disk, that a more massive star might have a more massive protoplanetary disk. And so then, therefore, you could form more massive planets in that disk, and that you might also have more debris, you know, later in the later stages also have more debris present in that system. So the Grand Tack is, getting to our system, the Grand Tack is also looking at the sort of early stages of the migration of the giant planets. So there was still subsequent outward migration of the giant planets after a lot of the Grand Tack scenario is supposed to be for. And some of that may have been happening around the same time period that we are observing in HD 95086. So some of that later stage stuff. So not as much migration driven by the protoplanetary disk, but more migration driven by the planetesimals that are left over from the fact that you've already formed most of your planets.
Okay, Rick, you have questions online?
Yes, this question comes from Alex Witza, who's reporting for Nature, and it's for Karen Meech. She asks, can you walk through the time scale of when exactly these inner solar system objects might have been tossed out into the Oort cloud?
Well, this again is referring to the Grand Tack model. This would have been early on as the giant planets migrate in towards the sun. They drag icy planetesimals from about the 8 to 13 AU region into the asteroid belt in the vicinity of the terrestrial planets. And then as they migrate outwards again, they're dragging the inner solar system material outwards. So it would have been very early, the first few million years in the solar system's history. I think one of the interesting implications of this is that it gives us some idea that some of these models are actually correct. There's several models that explain the formation of the early solar system in the terrestrial planet realm, and to get some ideas of which of these might have supporting evidence is interesting from the point of view not only of what goes out, but how we get volatile material into the terrestrial planets in the habitable zone. So I think it's exciting implications from that point of view also.
And then I have a question myself, Rick Feinberg, AAS press officer for Marc Buie. You mentioned that the similarity in the shapes and sizes of the two components of this binary asteroid imply that it may have formed as a binary as opposed to become a binary later. I'm wondering if you can walk through that rationale a little and tell us sort of what percentage of binary asteroids are thought to have formed as binaries versus to have formed as a result of collisions and stirring up of the asteroid belt.
Sure. Most of the evidence for this comes from the Kuiper Belt itself, not from Jupiter Trojans, because we've only got the one example. But if you study the properties, physical properties of the Kuiper Belt binaries, just step back and look. Basically, there's kind of two kinds of satellite systems, if you think of that as a satellite. There are large mass ratio objects, so think of Gaspar and Ida, where you've got a reasonable size asteroid and it's a tiny little chunk. The other kind is the binary or double asteroids, much like Patroclus and Menoetius. Okay, so a lot of the theories about formation seem to make a lot of sense from the framework that when you have the large mass ratios, those are typically collisions. And that's just the result from the collision process, and you just capture something afterwards somehow. And then for the nearly equal sized objects, it's hard to explain some of the other observables if they're coming by collisions. One of my favorite data sets on this is a survey of colors of objects in the Kuiper Belt, and particularly the binary components. And it's a great piece of work published by Susan Benecke and her team, where they measured the colors of the components. And what you find is that of all the objects that they measured, the colors of the average color of the systems has the full range of color that you see in the Kuiper Belt, from neutral to red and in between. If you look at the colors of the individual components, whatever color the system has, that's the color of the components. You never find a neutral one and a red one at the same time. The only way that you can really explain that is if they form at the same time. And they're in the local region where they were forming and accreting, they were made of the same material. And then there are various changes in composition. So, I mean, it's from that framework that I make the statement that these two objects probably were, in fact, coeval. They formed at the same time, and you would kind of expect that the properties would be the same.
Okay. Any more questions?
No more online. I'll just mention that JPL has posted two press releases, one on the HD 95086 system and one on the Cassini lakes and seas. So those are up now.
Any questions in the room? If not, thank you, and we will see you guys again tomorrow here at noon. Thank you.